Good morning. This next video, we are going to look at another derivative rule called the chain rule, and we're in section 2.4 of the textbook. So the chain rule states that if I have a polynomial, p of x, and it equals f of g of x, so basically a function g of x is inside of the function f of x, and both f of x and g of x are differentiable, right? Meaning that we can get the derivatives of both. Then to get the derivative, p prime of x, we would call it, right, would equal the derivative of f of x multiplied, and then you leave the inside alone, multiplied by the derivative then of the inside. And so we will obviously do many examples of this. And now there's another version here called power chain rule. But just to add this, just to add to this here before we move, let's say that we have a function within a function. Like I said, I have a function g of x, and it's sitting inside the function f of x. So I have a function within a function, which is called a composite. When I have a function within a function, that's called a composite function. And I have an inside function and an outside function, right? So here, the inside function of this example here, the p of x example, so that we kind of know how to separate them. The inside function is what's within the brackets here, g of x, right? And the outside function is f of x. And just in this particular case, the x value here happens to be g of x in its place, right? And we call it p prime of x. If you wanted to write that down, that's called p prime of x. So the outside function is often powers. So that's why we're going to look at the power chain rule next. So the power chain rule here states, again, if I have the polynomial p of x, and it's equal to g of x, now all placed, right, square brackets around it, all placed to the exponent of n, and obviously g of x, we can get the derivative of, is differentiable, and n is a constant, meaning just a number, right? So n is a constant, meaning just a number. Then to get the derivative of that, p prime of x, we bring the constant out in front, leave the inside alone. We minus 1 off of that constant, leave it as an exponent, and then multiply. Then we take the derivative of the inside. So for the power chain rule, number 1, here I just want to write down for this particular example that g of x is the inside function, right? G of x is the inside function. So then what would the outside function be here for this generic example here? It's actually n, the exponent. So n is the outside function. Okay. And basically this is like the power rule, right? Similar to, and then we'll go over an example. Okay. Let's move this up so I can have as much room as possible here. So here's an actual example here. We'll leave the instructions up here. So for the polynomial, p of x is equal to 5x minus 2 to the exponent of 4. Our 5x minus 2 is obviously the inside function, right? I'm just going to put here inside, not to write as much. And our exponent of 4, our n of 4, is the outside function. So if we look at, here are the rules to get p prime of x, the derivative of p of x. I bring that n value, the constant, out in front. So I'd bring the 4 out in front, leave g of x alone, leave 5x minus 2 alone, take 1 less, subtract 1 from n. So subtract 4 minus 1 would be 3, leave it as an exponent. And then I'm going to multiply. I'm just going to put here a dot just so you don't think it's an x or anything, right? Since we have x's in there. And I'm going to multiply then by g prime of x, which is the inside. So here, sorry, g of x is the inside, right? F of x is the outside. So multiply by the derivative of the inside. So how do I take the derivative of 5x minus 2? So the derivative of 5x minus 2 would just be 5, correct? Because that, you could put it in brackets or not, because that would be like bringing the 1 in front, then x goes to the power of 0, which x to the 0 just turns into 1. And anytime you have a constant, the derivative of a constant just is 0, and basically just goes away, right? And then we're just going to clean that up. So what I would do is take the 5, they're both constant, right? The 5 times the 4 and make it 20 multiplied by 5x minus 2 to the exponent of 3, and that's as far as you need to go. So what we've done is we've taken the derivative of the outside power by bringing the 4 over in front and then making it to the exponent of 3, 1 less. We left the inside alone, which is the inside, g of x. Then we multiply it by the derivative of the inner function. Then we got the derivative of the inside, which is the g of x part, which is the 5x minus 2. Okay. Now we're going to look at another example called Leibniz's notation. So if I were to have something that looks like y equals f of u, a function with u, and u equals g of x. So basically here, this g of x is in place of u, right? So that would be the same thing as f, and instead of u, I would have g of x. So again, we have a function within a function, right? Excuse me, and they're both differentiable. It's always that we can take the derivative of both. Then Leibniz's notation is dy dx just means taking the derivative of y with respect to x would be equal to, see, if I'm taking the derivative of y here with respect to x, but there's no x's in this particular function, right? I have to take dy du, I have to take the derivative of y with respect to u, then multiply that by du dx. Then look at this function, the derivative of u with respect to x. So again, we'll go over an example of this. So like I said, we could have made it f of g of x, and then it's a composite function, just like we just did. But for Leibniz's notation, it's basically that we're separating the two and we're doing the two separately. So this is, again, just a different way of doing an example like this that's not the same as above. I'm showing you a different way. So the inner function is the u, and we're spreading it into two functions where u is now g of x. Now, if you take a look also before we start at the fractions here, we do need it to stay this way. Like I know if you have a numerator and denominator that are the same, right, then you could just cancel them out. So you could see this du over du. Please don't copy this down, and you might think, okay, well, du and du, I cancel those out, and then I have dy over dx, which is the same as the left side. But we don't want to do that because we want to be able to differentiate this separately and then this separately in order to do this particular kind of question with Leibniz. Okay, so just leave it the way that it is. So let's look at an example. If I have y equaling x to the power of 4, and if I have u Now I'm just seeing here, u equals 5x minus 2. There is no u here. So this should say y equals u to the power of 4. So let's just, I can't erase this exactly on here, right? But let's just write, it really should be y equals u. Sorry, just correct that to the power of 4. Or maybe it is corrected on your worksheet already. And then u, right, within that is really 5x minus 2. Figure out dy dx, differentiate using Leibniz's notation. So I'm just going to color code here. So in order to figure out dy dx, just to put over here off to the side, dy over dx, that is going to be equal to dy, differentiate y with respect to the first variable u, and then I'm going to multiply that by du with respect to the other equation has x in it, so du dx, okay? So I'm going to differentiate basically both separately. We're going to look at each one separately. So let's say just to color code here, let's do green, dy over du. So that would be this one here. We're getting the derivative of y with respect to u. So dy, and then we'll multiply them separately. We'll multiply them together afterwards. So dy du would be, to differentiate, this would be 4 in front, then u, and then 1 less on the exponent, right? 4 minus 1. So that's it. And then to color code the other one, we're going to get du over dx, differentiate the function of u with respect to x. We're looking at just this equation. So that derivative again would just be 5, right? Just like it was before. So now all I'm going to do is put them together. So here, multiply the green and the blue together. So I'm going to go back here and say dy dx, which is another way of just saying, let's say y prime, right? So dy dx is equal to dy du. Dy du is 4u cubed multiplied by, again, 5. Now, again, if you wanted to put both of these in brackets, you could. And then that answer would be 20u cubed. So that is our derivative. But it's asking us to get dy dx, right? So it's asking us to get the derivative of y in terms of x. And if we look at, this is dy dx, but we have u on the right-hand side here. There's no x's. So we do want our equation to be in terms of x's. So we need to then convert, if we look up here, u is equal to 5x minus 2. So we're just going to replace u with 5x minus 2 so that the derivative has x's in it like it's asking us to get. So then that would be equal to 20. And then instead of u, replace u with 5x minus 2 and then still cubed. Okay. And if you notice, this is the exact same answer as our power chain rule was up above. So that's just showing again how there's 2 different ways of doing this question. You just have to pay attention to if it's asking you to use Leibniz's notation or by using the power chain rule. Okay, so just be careful with that. Let's do some more examples. I'll try to fit everything in here. So differentiate, right? Or it might say determine f prime of x. So get the derivative is what it's asking us to do. So I have f of x equaling the square root of 2x minus 3x to the power of 5. So this is a radical. And in order to differentiate, we want to change the radical into a power and have it in exponential form first. So what I would do here is, for example, let's just put over off to the side. This is not part of the question, right? But the square root of 9 would be 3. That's equal to 9 to the power of 1/2. If you were to try that on your calculator, the square root symbol is the same thing as being to the exponent of 1/2. So then therefore we could make this, use brackets, 2x minus 3x to the power of 5. The power of 5 is only on the x bracket, all to the exponent of 1/2. So the inner function is the 2x minus 3x to the power of 5. The outer function is like x to the power of 1/2 is your power of 1/2 there, right? So in order to get f prime of x, what we want to do is bring the 1/2 out front, leave the inner alone, and then we want 1 less. So we have 1/2 minus 1, or like 1/2 minus 2/2. So you should have there -1/2 as an exponent. And then we want to multiply that, right, by the derivative of the inside. So the derivative of the inside here would be 2 minus 15x to the power of 4. And again, you could put brackets around all of that. 2 minus 15x to the power of 4. Now, I know that this might seem silly to you because in order to get the derivative, we had to change it into an exponent. But then when we're basically cleaning up our answer, we do want to have it show the same way that the original question was. So we do want to put the radical back in. So just make sure that you're answering by changing it back to the original question and putting it back into its original form. So here we have the half, we'll copy down the half, but we know if we have a -1/2, if it was a +1/2, I could just put a square root around it, right? A radical sign. But because it's negative, I have to put 1 over that. So let's put brackets here in order to change it to positive, right? So 1 divided by the radical sign of 2x minus 3x to the power of 5, again, multiplied by 2 minus 15x to the power of 4. And since that's a fraction, I mean, you could think of it as this is over 1. Sorry, this entire thing is over 1. And then if you were to clean that up, if you were to multiply all the tops together, all the numerators, I would just have 2 minus 15x to the power of 4. These are not like terms, right? I can't go any farther. Divided by 1 times 2 is just a 2 in front. And then the radical sign with 2x minus 3x to the power of 5. Now that would be as far as you can go. Okay, so again, just make sure you're kind of working with me, or let me know if I need to pause, or pause it if you're watching this at home or for a second time, because I'm going to have to clear this because you'll get to know my writing's a little sloppy, and hopefully when you're writing these down for calculus, there is many steps for every question. So just try to write as neatly and not as small as you possibly can, but don't write maybe as large as you would have in grade 9, 10, or 11, because you know we need more steps here. So I need to clear this so I can have more room for B. All right, so for B we have m of x equals 1 over x cubed minus x, and then in brackets cubed, so the whole bracket is cubed. So again, in order to make this so that I can differentiate it, I should have this power up in the numerator position. So if I move it up into the numerator, it just makes the power negative, right? So then I would have here, I could leave the 1 in front technically, right? But you don't have to. And then I have the bracket x cubed minus x, and then simply the cubed would now be to the exponent of -3 if I'm moving it up to the top right, to the numerator position. So now you need to do that first before you get the derivative of m of x. So m prime of x is equal to, again, same thing, bring that exponent out front, so -3, leave the inside alone, x cubed minus x. Now be careful here when you're subtracting 1. -3 subtract 1 is a -4, right? Multiplied by then the derivative of the inside. So 3x squared, right, minus 1. Because that 1 here of exponent would go in front, and then you'd have x to the power of 0, but the 1 would still be there. Now it's just a matter of cleaning it up, right? So I would have here, I don't like negative exponents. So if I keep the -3 on top, so if that exponent is negative, I actually need to move this, just to change the color here. I need to move basically this entire part here down to the denominator to make it positive. But this part is positive, so this part can stay. So I would have -3 still multiplied by the second bracket, 3x squared minus 1, divided by, and just be careful that you don't miss any steps, moving this down to the bottom, x cubed minus x, now to the power of +4, so that everything is positive. And I'm just taking a look here. That would be as far as I can go, right? So let's take a look at the next example. Go one step a little bit more difficult here. Moving this up. Okay, so what do we notice here? Again, first thing the same as B is I need to move. This is to the power of 1/3 if I were to get rid of the radical, right? But I need that to go up as a numerator in order to differentiate it. So I'm not going to say y prime yet. I'm just going to rearrange this first. So y would be equal to 6, and then I have a bracket. What would be inside the brackets is x squared plus 4. And then that cubed root out in front would really be to the exponent 1/3. But because I'm bringing it up to the numerator, it's actually to the negative 1/3, correct? So what do you notice that's different here? Now I have a coefficient in front. So just to point that out, now I have a coefficient of 6 in front, which I didn't have before. But basically the rules would be the same, right? In order to get y prime, the derivative of y, leave the 6 alone. It's kind of just hanging out for the ride. Bring that negative 1/3, right, out in front. So it's going to be 6 times the negative 1/3 now, which would be like 6/1. Leave the inside alone, just like we did, the x squared plus 4. I'm going to subtract 1 off of this exponent. So negative 1/3 subtract 1 is like negative 1/3 subtract 3/3. So you should end up with negative 4/3. And then we're going to multiply that by the derivative of the inner, the derivative of the inside, which is 2x. Right? Because whenever I have a constant, that's just plus 0. We don't need to add 0 here. So the derivative of the outer is here, bringing this negative 1/3 out front, minusing 1. And then we have the derivative of the inner over here at the end. Now it's just a matter of cleaning it up, right? So I have y prime. Why wouldn't we multiply? Let's multiply, right? Again, if you wanted to put a circle, 6 times -1 over 1 times 3 would be -6/3, which would end up condensing down to -2. So I have -2, just to go slow here, x squared plus 4 to the exponent of -4/3, all multiplied by 2x. So as well here, I could do the -2 multiplied by 2x and put those together. So I'd have -4x, just to make things look as simplified as possible. And then you know the rule, hopefully by now, we don't want to keep that. That should be a little bit higher up. I just kind of don't have space here. The -4/3, right? We don't want to keep the exponent negative. So we need to bring it down below. So the -4x would stay on top. Put my divide sign. Then I would have, now we have to be careful here. I'd have my, okay, let's just do it in steps. Let's do x squared plus 4, bring that fraction down and just make it +4/3. But again, like we've also said, the original question had a radical sign. When I'm answering, and this is y prime all the way down, when I'm answering, I want to change it back to a radical. So this would be a radical sign with x squared plus 4 underneath. And then what do we do when it's an exponent of 4/3? The denominator, if you remember from grade 11, the denominator is what's out in front, 3. And then this would be the numerator of 4 would be inside underneath the radical sign. This bracket would be to the power of 4. So it's x squared plus 4 to the power of 4, and then all cubed rooted. Okay, if we need to go over that. let's do one more example that also is a little bit different. So here I've done an example of a constant that's out in front. Here, if you look, I also have a value that's out in front, but it's not a constant, right? This has a variable, it's x squared that's out in front. So what would I do here? So what I want to do is I want to get the derivative of the first, multiply it by exactly what's there as the second term, then get the derivative of the second term, which would be this term, right? And multiply it by the first term. So I have to divide this up and separate it again into two terms. So we're going to use the product rule to complete this question. So g prime of x, hopefully I have room here, sorry if I don't, is to get the derivative of the first. Well, the derivative of the first would be 3x squared. And then again, multiply that by whatever's there as the second term. So I'm just copying this down, 8x squared plus 1 to the power of 4. And then to that, don't forget we're going to add, when we have the product rule, to add the derivative of the second first. So the derivative of the second would be bringing that 4 out in front. Ignore the x cubed right now. Leave the inside alone. 1 less would be 3, but then don't forget I have to take the derivative of the inside, right? So that 2 times 8 would be 16x times 16x multiplied by 16x, and then copying down, multiplying that by the first term, x cubed. So again, just to go over, what we've done was we've taken the derivative of the first, copied down the entire second term. Then we add to that the derivative of the second term, which is in two parts, right? We have to take the derivative of the outside, leaving the inside alone, and then take the derivative of the inside. But then don't forget to multiply by the first part. That's just the original that we're not getting the derivative of, right? If you need to write that down. And now it's just a matter of basically cleaning it up if I can. So here I would have 3x squared. There's really not much I can do with that. And then I have the 8x squared plus 1 to the power of 4. Again, not much I can do with that right now. And then adding to that, I have my 4 and I have my 16x here. So I could do 4 times 16, right, would be 64. And then I also have the x multiplied by x cubed. So again, same bases. When you're multiplying, you add the exponents. So it'd be 64x to the power of 4. And then I have the 8x squared plus 1 to the exponent of 3. So these are all multiplied together. These are multiplied together, and then I have the plus sign in between them, right? So I'm just going to look here first. So what will usually happen is now you want to look at if there's some type of factoring you can do. So I'm just going to write down for this one. Let's look at my two terms and if there's anything common between them. So this is an entire term, right? Terms are separated by plus or minus signs. So everything multiplied together is 1. Everything multiplied together is a separate 1. And if you take a look, don't you see that the 8x squared plus 1, 8x squared plus 1 to the exponent of 3, because you take the lower exponent, right, would be a common factor. And between the 3 and the 64, is there anything common that I could take out there? Maybe not numerically, but I also have the x squared and the x to the power of 4. So I could at least take an x squared out. So a common factor between these two terms would be x squared. And then my 8x squared plus 1, again, to the exponent of 3, right? You take out the lower exponent and then square bracket, right? I call it leftovers. What would be left over? So I still have the 3 and I have one of these. So I would have 3 bracket 8x squared plus 1. Sure, you could put it to the exponent of 1, but you don't need to. Plus, I'm on the second term now. I have 64, I haven't taken out, and then x squared. And I've taken all of the 8x squared plus 1 to the exponent of 3. I've taken all of that out. So now I can close my bracket. Now, is there any cleaning up, tidying up that I can do here? So I have the x squared I have the 8x squared plus 1 cubed. And I could take the, let's do distributive property here. Let's just write this out. Distribute the 3 into the bracket. So 24x squared plus 3 plus 64x squared, if that might help us out a little bit. Well, it creates like terms, so I can put those together, right? So then my next step here would be x squared, the 8x squared plus 1 cubed multiplied, right? We're all multiplied now by 24x squared plus 64x squared would be 88x squared plus 3. These are not like terms, 88x squared plus 3. Now I cannot go any farther. So that is my derivative of g of x, differentiated form of g of x, using the product rule. Let me show you the next one here. Actually, I think we just have one more. And it is another example of using Leibniz's notation. So that would be numbered just the bottom of page 1. We've done the first example of that. So use Leibniz's notation, applying the chain rule to determine dy dx, and then evaluate it after it's differentiated for x equaling -2. So here are my basically two terms, right? I've got y equaling 2u minus u cubed, but u itself is equal to 1 over x. So again, here we have two parts. So we need to look at this as, I'm just going to erase this so I have more room here. I have this part here. Oh, not on my drawing tool. I have this as part 1. And I have this section here as part 2. So I'm going to get you started, and then I'm going to leave you for a little bit to see, just to try it on your own, see how far you can get. Obviously, you're always using pencil for math, and then I will play the video back and we'll see how you did so far. Go as far as you can. So again, to figure out dy, the derivative of y with respect to x, first I have to get the derivative of y with respect to u, because that was my first part, right? So the derivative of y with respect to u, and multiply that by the derivative of u, which is the second part here, with respect to x. And that will end up giving me dy dx. Then I have to evaluate, right? But first, let's just get the derivative here. So I'm going to let you, I think you guys could get the derivative of the first part and the derivative of the second part, dy du, right out here to the side, and du dx, right out here to the side, and then maybe go as far as multiplying them. And then we'll see how you do from there. Okay, then we'll play the video back.